Welcome to the Uptime Wind Energy Podcast. I'm your host, Alan Hall, along with my co-host, Joel Saxum. On this episode, we're addressing a critical issue that is plaguing the wind energy sector, the problem of failed blade bolt inserts in wind turbine blades. And these failures have a significant concern for wind energy operators, leading to downtime, costly repairs, and the potential for liberated blades. Our guest is Edo Kuipers, owner and engineering manager of We4Ce. And We4Ce is based in the Netherlands. We4Ce offers a range of services related to the design and engineering of wind turbine rotor blades. And they have designed an upgraded blade bolt insert that can be retrofitted in the field. And this new insert product could dramatically lower a wind turbine operator's downtime and blade repair costs. Edo, welcome to the show.
Thanks for having me here, Alan and Joel.
So this is a really interesting product, but first I want to get to how big of a problem do we have in the industry. And Joel and I have been traveling around the United States quite a bit, and pretty much every farm we stopped at had blade bolt insert issues. They didn't know why they were having them, but they had them, and they were deeply concerned about it because of what could happen to the turbine. And Edo, are you seeing the same thing? Are you getting a lot of reach out that way?
Yeah, more and more we see this. I think in 2021 we were contacted by the Indian market for the first time. Those were 40-meter long blades, 1.5 megawatt platform. And those blades were like 13 years on the turbine. And then all suddenly started flying off, basically. And more recently, this is popping up basically, not after 13 years, but after 6 years, for example, already on a 2.x platform. So, yeah, we have been contacted first on the Indian side. We have seen it in Brazil. We have seen it in Thailand, for example, also. So it's more and more addressing the problem. Also from the Northern American, we have the first contacts running.
So I think that if we describe basically the breadth of the problem, right? So there's when you bolt the blades on, and if you're a wind technician, you know this stuff, right? You've seen it, you've done it, you've been around these things. But for some people that aren't as technician minded, you may not know exactly what the problem is. But what it is basically when you bolt the blades onto the hub, there's all these studs, right? And the studs come through, or the studs stick out. You stick it into the receptor on the basically on the hub, and then you bolt them on. But if where the stud connects into the blade doesn't stay true to its design and becomes loose or starts to move, well, then however well it's bolted doesn't matter at all.
Correct. Also, it's not a bolt problem. It's the connection between the steel bushing itself. This is like a plug in the wall when you hang up a painting, for example. This plug in the wall is getting loose from the laminate.
All right. So if the inserts are becoming loose, what's the scale of what we think the scale of the problem is? Is it like 50% of blades have this issue, 20% of blades have this issue? It sounds like it's more than 10% at the moment.
It can be. What we've noticed that in the past, blade designs had quite a lot of safety margin in them. And what we've seen is that, in time, as wind energy, we are reducing our margins. And because we are losing, these margins are getting closer to 1.0, let's say like then, where we had in the past like 1.5 or 1.6. These margins are getting lower, and then the chance of loose bushings is also getting earlier with let's say the 2.x or the 3 megawatt turbines, if you build it in exactly the same way, of course. And I'm not sure, we don't know if the manufacturer has built it always throughout all these years in a consistent way. We don't know that, of course. The only what we can do is observe what we see now. And what we see now is basically, first of all, the reserves or the mass moment, basically, the mass is getting higher with the given pitch circle diameters. Longer blades remain on the same pitch circle diameter with the same number of bolts for longer distances of rotor blades. So lower reserve margin, that's one of them already. What we then also noticed, because we did like 3 root cause analysis projects on different locations in the market. And what we noticed is that in all these cases, it was concerning polyester blades. It was concerning a special mat, which was basically wrapped around the bushing as an interface material. and this mat had, what we have seen, an irregular distribution of the polyester resin in it. And it had these dog bone shaped, it was prefabricated parts in there. And what happens there is basically due to this irregular distribution of the polyester resin, we get differences in curing cracks, basically, or curing features. Polyester resin is more sensitive to curing cracks, shrinkage cracks at the curing than an epoxy is. And if you then have this irregular distribution of your resin around these bushings, then you can also imagine that on different locations you get these micro cracks already from the start. And then it depends a little bit on the reserve factors which you had from the start, how long this will last. So what happens is, due to these micro cracks, we are losing a certain amount of the bonding area, of the area that has to transfer the loads from the tip to the pitch bearing, for example. If we are losing this load carrying area, that means that the stress levels they are going up, they are rising. And when we realize that there is a non-linear relation between stress level on the, let's say, on the vertical axis of your diagram, and your lifetime on the horizontal axis of your diagram. This is not linear, but it's, let's say, a logarithmic. And realizing that if you are losing, let's say, like 10% of your area, of your load carrying area, and or with other words, if your stress levels are raising with 10%, you can already lose like 50%. You can halve your lifetime already.
Edo, if I have a polyester blade, how would I know I have this defect in the blade? Is there any way to detect it before the insert becomes loose?
When you're a park owner, you have always these 6 months inspection intervals or 1 year inspection intervals. Then you go inside the hub, and there's let's say like a sealing done between your blade root and your pitch bearing. This is this little line with sealing component filler. Check for cracks in that area, especially on the trailing edge, for example, and on the leading edge. If you see there are some kind of cracks inside, then cut it away with a knife and go with a filler gauge inside. Check how the distance is, and do it on different pitch settings. So turn the blade, different pitch orientation, and see again this distance. Then you can measure if there is a variable cap going on, yes or no. And if you see a variable cap, for sure you have some way a loose bushing there. Especially check for the trailing edge and the leading edge.
Is there an audio component to this? Like, can you hear it when the turbine is running? Can you hear the blade shift around a little bit? It's such a massive load. Is it making noise?
No, I don't expect that. I don't expect. Maybe a little bit on your torque drives, you could see it in the pitching because you have a little bit more sweeping forward and backwards of your blades. But then you're already really far, then you really have huge loosened bushings. But you can imagine that the pitch inertia changes in that respect, so you will feel it on your pitch drives. But I guess, okay, apart from that, the blade has then not flew off yet, but you're already too far. It's already too far off.
Well, and that's the question I want to ask. I want to get into here a little bit is okay. I'm asking from an operator standpoint. So if I'm an operator, if we're doing a yearly inspection or end of warranty or whatever that may be, and we discover some of these gaps, or we go, oh, we're suspecting that there's something going on here. What is that? Basically, the delta in time between. I know you can't say it's 16 hours or 22 days, but what does it look like? I mean, do you have, if it starts to loosen up, does an operator have a year or do they have a day? Like how long before a blade decides to come off?
You have to ask a blade, but it depends in the mood. Maybe when it's autumn earlier than it's spring. Not sure about that. But no, we have had these monitoring systems also, are not us, but our customer have some kind of monitoring system. Try to expect exactly what you say here, Joe. Try to monitor how long do we have. It's not years, it's not days, but it's like 2-3 months, I would guess.
That's kind of what I would think too. Like once it starts loosening, because at the end of the day, what you're trying to avoid is catastrophic blade failure. Blade breaks, blade takes down the tower, the whole thing can come down, or you liberate a blade. Safety for everybody, aside from the financial loss in the wind farm. So there's a lot of, this isn't like, we have some leading edge erosion and we need to get it fixed at some point in time. This is a big problem that, like, if you're seeing the early signs of it, you need to address immediately.
Absolutely, totally right. And the sooner you address this, the better it is for the repair as well. Because what we also noticed, what we are doing is with one customer, this is basically the launching customer here, it's in Asia. What we're doing is we're checking at different locations of your blade root. What is the capping? So what is the variable capping? Let's say, is it like 0.2 millimeters variable capping? That's the values where we are starting to talk about. Or is it also 15 millimeters variable capping? That's also what we've seen. So we are trying to distillate the remaining strength of when the bushing is already, let's say, loose from the laminate with 15 millimeters. What is the remaining strength? And what is the remaining strength if it's only 0.2 or 0.5 millimeter loose? We are trying to quantify that to get a repair qualification scheme. Let's say it like that. Hey guys, if it's like 0.5 millimeters, yes, lower down the blade, it makes sense to repair. But if it's already like 5 or 10 millimeters, of course, also lower it down. But there's not such a good chance that there is a suitable repair because there is already so much damage going on in the surrounding area with all the other materials.
Yeah, with all the movement. Yeah, I get it. And I think something important to touch on there for just one bullet point is you guys we're talking about a solution that you have, but at the grand scheme of things, what We4Ce is, and you guys have been working in the sector for a long time, you are root bushing specialists. So this isn't just like something that you've dreamed up a one-off product. You're good at, you're a consulting firm, you've designed blades for or helped put things in manufacturing facilities and all kinds of stuff.
Correct. Since 2008, early 2008, with the first blade design, because we are not only the root expert here, if I may say so, but we are a blade design company for aerodynamic design, structural design, etc., etc. So in our first design, from the start, we decided, okay, when we want to do this, we are going to do it with our own bushing development included. So, and that started with the M30, so the metric 30 millimeters size of bushings, suitable for M30 threaded ends for the 1.5 megawatts. And then we developed that through the years to M36, which is quite popular in most of the turbines now, and also M42 we have fully certified. So indeed, based on this idea of the bushing, when we encountered the problem, we thought, okay, come on guys, we know quite well what we are doing with our own bushing for new blades, although they are in epoxy blades, I must say. So let's find here a solution. Let's alternate, or let's change our bushing, for which we have already so much testing coupons and test data available. Let's alter our solution for having a solution for, let's say, the retrofit.
So the problem, Edo, is that the repair side, and you have these inserts, you've been putting inserts in blades for a long time. But if you have an existing polyester blade and you need to do a repair today or 6 months ago, what does that process look like? Is it even possible to make a repair without basically tearing the blade hub apart, the root of the blade apart?
That's where we started with. In 2021, this first customer, we started with grinding open the root. We said, we don't have a solution, just grind it open, use your grinder. It's really labor sensitive. There's a lot of dust going on, of course. It's not nice for the people underneath the sunshine of the Indian sun. Let's say it like that. It's also the quality where you're ending up is really depending on how the person is doing the scarfing, for example. We also even have seen problems after these repairs that somebody did not do a proper scarfing job, for example. So you really need to take care who and what is going on there and who is doing the job. At that time, we said, okay, we need to automate this. So, and we also need to concentrate on where the problem is. So when there is now a new customer popping up there, we always say we start with the root cause analysis. So we go up there, we take a piece, we do some, preferably a hydraulic puller test if needed. Preferably we cut down some roots and bring them to our office. We see if it is actually an interface problem, what we see many times. Is it really an interface problem of the bushing with the surrounding laminate or not? If it is an interface problem, then we can offer a solution here by taking this interface layer out of it. We are using a drilling machine. We are having a cooperation there with a company called CNC on site in Denmark. They are really the experts in drilling. They are doing a good job there. And then once this hole in the laminate is created and the old bushing is thrown away, let's say it like that, then we have a clean situation. Interface layer is there anymore, is present anymore, and then we can come up with our own bushing, which we modified for a special infusion process on site. So then we implement our bushing in there, and we do an infusion strategy by infusing it from the front. We call it, it's a repair by means of front infusion technology. It's, let's say, like a big bushing, and we have a steel part and which is wrapped around with all kinds of roving, and it has a hollow threaded end. So what we are doing is we are implementing this steel bushing with materials around it. We are implementing that in the hole that has been created, and we are vacuumizing it here. We are vacuumizing it, the bushing at the front. There's a special flange. And we have a hollow threaded end, and we are infusing, not injecting, through a hollow threaded end all the way to a dispenser at the back on the tip side of the bushing. And then gradually the resin will be pulled around this bushing with roving around it to the front. So it is a really a controlled process what we are doing there, from the tip infusing to the root side. And once the resin is coming out of the front where you have the vacuumization connection, then you know that it's almost full. You also have to go into the depth of the roving, and so you leave it for a while. And this process takes, let's say, like 30-40 minutes, and then it's basically full.
Okay, so CNC on site cleans out the existing bushing insert, creates a standardized clean hole. Your new product, the We4Ce insert, is then slid into this clean polyester hole, and you're injecting. Are you injecting polyester resin or infusing? I don't want to say injecting. You're actually pulling a vacuum and pulling it through. Are you putting polyester resin back in, or are you using a stronger structural epoxy to attach this insert?
We tried it with polyesters, and it did not work. We do it with epoxies, and it works. It was great. It's much stronger.
So the roving, the fiberglass you have wound around your steel insert, when that becomes infused with epoxy, is then a new structural member of that blade. And how strong is that once it's installed versus the OEM insert?
The good thing is that we are taking the certification body along with it. And so far, they are saying it is equal or higher in strength than the original one was.
Wow. Okay.
I must say, Alan, the more you test, the more you learn. And sometimes you do, let's say, these tasks like 3 steps forward and 2 steps back again. But as long as you know what was going on with this testing, then you can then make the next step again. So for sure. For sure, I'm still saying it's good. It's as equal as the original one is. And even if it would be, let's say, 10 or 20% lower in strength, it still is good enough to have the remaining years on the turbine. We are going for, let's say, like 15 to 20 years. The original one is always going for 20-25 years. So even in that case, it would be, for me, it would be satisfying. It would be good enough, because our target is quite high. We are testing with a bushing which is our strength results on the testing are with the bushing which is smaller in length. It's around. I should wear my gloves here. It is with, let's say, a 60% bushing length from the one which we are going to implement in the real life later on. So we are basically already 40% more conservative with our results.
So the new insert and the approach you're taking, which makes tremendous amount of sense, by the way, if that can be installed on site, right? So you would take the blade down so you can CNC machine, clean out these holes, do the infusion, put the insert in, do the infusion, vacuum, pull through the epoxy, let it all cure up. That's essentially it, right? So you're not replacing all of the inserts typically. How many on a blade are you replacing percentage-wise?
I would say we are now having, let's say, a blade which has 92 bolts, bushings, and we are going to. The idea is now that we are going to replace like 15 to 20 on the trailing edge and 15 to 20 bushings on the leading edge, because it's not fully trailing edge, it's not fully edgewise loaded, but it's a little bit between flapwise and edgewise in. So this is where we start.
So that's good to know, because I think a lot of operators right now who have this problem think, I have to replace every single one of these inserts. Oh my gosh, that seems like a tremendous amount of time to do this. But the engineering says no, right? The loading and these inserts are failing on the leading edge and the trailing edge, essentially. So we're going to fix those, provide more strength in those, which is going to stabilize the blade. Isn't that the approach?
That's the approach, exactly. This is an interactive decision, basically. So what we are going to do is some testing with hydraulic pulley system together with our customer. At the moment, the most suspicious ones are at the trailing edge and leading edge side, due to the high mass moment loading. But for example, if the highest loaded would be exactly at the trailing edge, and the first 4 would be the most suspicious one, then we always do 1 or 2 or 3 extra, of course, on the side. But if flapwise loading for this turbine is non-issue, then don't replay that. I mean, if you go to the dentist, I mean, if you have a toothache, I mean, he's not replacing all your teeth, right? You're concentrating on the problem area. So.
Yeah, that's true.
Yeah, so Edo, one of the things, again, from the operator standpoint is it's going to be replaced in cost. So I know I've looked at some of your materials, and it looks like if you were to do a blade, you're depending on the level of repair, 30 to 50,000 euros per rotor blade for fixing, which is a lot less than a new blade, right? Because that's the alternative. If this thing's loose, these are loosening up. The alternative is, hey, we have to replace this blade because there's no other way to fix it. But you guys can do it. 30 to 50,000 euros a blade is kind of the conservative estimate. But how long does it take in the field?
10 days.
Oh, wow.
Because what we're looking at for a market here, of course, there's certain models out there that are having issues with this at early life, right? So there's some possible serial defect thing here in a couple of these models that we've been hearing about. But one of the other large looming things is, all right, the wind industry has been around since, it has been in big swings since the 90s, early into the 2000s. So there's a lot of fleet at a global basis that right now is looking for lifetime extensions. That's looking for, I know, the country of Spain, they just put something out that's like, hey, we're kind of in a hurt because we have a lot of our fleet getting to that 15, 20-year-old mark where we've got to decide what to do with all this stuff. So you guys are looking at a big market. What do you see that for?
We see the same. Once this is heading off, then I see a huge demand for this repair technology. Absolutely.
And for safe harbor blades, and a lot of operators in the United States have a number of blades in safe harbor for the time that they got to go swap blades, right? They have them just sitting on the ground. If you know you have this polyester problem, why are you not doing this insert while those blades are sitting on the ground, so that when you do deploy them, you do not have this failure out in the field? Because that's the point of safe harbor at the moment. And that seems like the almost the perfect situation for the We4Ce solution is blades are already on the ground that we're going to be deployed pretty soon. Does that then it help fix this problem before it gets out in the field? Like, we can fix these blades on the ground, right?
Yeah, and you need to have the blades on the ground. It's not an up tower solution, unfortunately not. That's not possible. I don't see that working. So we have to hoist them down. And the nice thing is also, once you have them down, you can also do an aerodynamic upgrade if you want. You can also fix the leading edge erosion issues, for example. We have now one customer He's having the problems already. He's ordering some new blades, of course. He's combining sets, so he's making from 3 turbines now 2 turbines. So we are because of each of the 3 turbines has 1 blade with loose bushings, so he's combining that to 2 new turbines. He's keeping them in storage. Until he basically receives the machine from us. So this morning I had a conference call with him. Okay, so when do we get the order? Then we can start building the machine. But he's nicely keeping them in place for us, so we can start with those already. And then at the same time, he can do the leading edge erosion maintenance and repairs on that one. Even if needed, an upgrade with the vortex generators or whatever he wants.
Strike tape, a lightning protection upgrade.
A lightning protection upgrade.
It makes absolute sense, right? So I'm thinking about this in the large scheme, right? Okay, because we're, of course, we work globally, but we're very focused on the U.S. market. So when I look at some of these larger wind farms here, I know some of them have a set of blades or sometimes 2 sets of blades at the O&M yard, right? So if they have one that has an issue and the crane is there, they'll take that down. If that's going to be out for 10 days, they might even just throw the other blades up. So if you're looking at a turbine, you're like, okay, this has got some issues. We could work on these things. Drop that one, put your good ones on, and then you're getting no downtime out of that turbine while you're on the ground fixing it. And it's just like recycle as you go.
That's what we're doing. And one of the biggest problems we will encounter, I guess, is crane availabilities.
Absolutely. Because that's, right now in the States, with how many are being built and how many, I say this too, Alan, we've been talking to a lot of people doing main bearings and pitch bearings. So there's a lot of cranes running around just dropping rotors and swapping bearings and going back up. So the crane availability, I know, it's tough right now in the States.
Yeah, in Europe, we are developing systems working with cables that we throw basically a cable around the hub, and then let's from the inside lower the blades. It's not our idea as We4Ce that we are doing the service job ourselves. What we want is we want to hand over the technology to the market. So we want to have a cooperation with service companies who want to learn the trick, and then we license the technology out to them, so that on different areas in the world, North America, South America, India, Thailand, for example, we have different groups where we work together with. So we educate them. So CNC on site is educating them on the machine. We are educating on the refit implementation process. So we transfer the know-how. We give, let's say, like 2 weeks, 3 weeks, maybe 1 month. We guide them until the first turbine has been repaired, for example. And then we move on to a next customer. And then, of course, the customers always can come back to us. But then this speeds up the process of the repair. If we want to do all in the house with a small group as We4Ce, we are not able to do so. It's also not the fun part of the work. The fun part of the work to provide new technology to the market.
So, Edo, this is a really interesting product, and it's going to make an impact, and already has made an impact. And we're going to see a lot more of these new upgraded inserts applied in the United States and Europe and all around the world. And I'm just fascinated by this because this is the kind of technology that we need today to keep wind energy moving forward. And I really appreciate you coming on the podcast and describing this to us, because Joel and I have run into so many operators that need this service. So congratulations, Edo, and thank you so much for being on the podcast.
Thank you very much for having me here. It's really an honor to be in this show, Alan and Joel.